Is there anything you found particularly difficult that you want to...
It's a bit lean to the side.
Okay. Is that better? Okay. Is there anything you found particularly difficult that you want me to go over today? Well, the exercises we didn't do from last week, someone got a copy of our show. Can I borrow your book?
Yeah, fine.
Sorry. Office. So 5, 7, 1, 2, and 7. So we did 1 was trivial, 2 we did, 7 we just started at the end of the lecture, then we were interrupted. So let's do exercise 5.7, question 7. Okay. Did anyone have a go at this? Does someone want to volunteer to do it on the board? Anyone? No volunteers? You're going to make me work for my money. Okay. Okay, so this exercise with a tax. Okay, monopolies. So there's a production, there's a demand curve which is P equals A minus Q. And there's some cost of production C positive, marginal cost. Excuse me. Okay, and the government imposes a tax of $T per unit of output. Completely in the way. Okay, so $T per unit. Okay, so if the monopolist sets a price P, then the consumer ends up paying a price P plus T. Okay, so first thing to do, let's invert the demand curve. Okay, so P is A minus Q, then Q quantity demanded is going to be A minus P. Okay, but this P is kind of the final price that the consumer pays. Okay, it's not the price that the firm is going to set. Okay, so in terms of the price that the firm is setting, let's call this PC for P paid by the consumer. Okay, and then we've got PC is the price set by the firm plus the tax set by the government. Okay, so this is A minus PF minus 2. That's their demand for the product. Okay, so what's the monopolist going to do? Well, the monopolist wants to maximize profits. What are profits? Profits are quantity times price minus marginal cost. Marginal cost for C. The monopolist is setting a price PF. Okay. Here's the quantity that's demanded of that price PF. Okay, it's A minus PF minus T. Okay, it's PF minus C. Let's see if we can use that trick that I showed you in the lecture to maximize this function. Okay, so without doing any differentiation, what's the maximum of this function? Or at least how would you find it? So this is just a quadratic again.
Like half of the intercepts.
Half of the intercepts, okay. And what are the intercepts going to be?
P.
Yeah, PF.
And
yeah.
C. Oh, sorry.
Yeah, C and A minus T. Okay, this is A minus T minus PF. So when PF is A minus T, this is 0, or when PF is C, this is 0. Okay, so the profit maximizing price, PF star equals the average of those 2 points. Those are the intercepts, the maximum must be halfway in between. So it's C plus A minus T all divided by 2. Okay, no differentiation. Super easy. So you can see that, look at the way the tax is entering the demand curve. The tax is just shifting the demand curve downwards. Okay, it's reducing the maximum they're prepared to pay for the good, effectively, because they would be prepared to pay A in the absence of a tax, a maximum of A. But with the tax, well, they've got to pay something to the firm and then something else to the taxman. Okay, so the maximum amount they're prepared to pay to the firm is lower. Okay, so here's our optimal price. So the tax is reducing the price that the monopolist can set. That makes sense. So does that agree with the answer in the book? Yeah? Okay, so we're the right way. Okay, the book gave another way of solving the same problem in terms of the working directly with the inverse demand curve, but I think this is clearer, right? It's easy to think about there being 2 prices at work, the price the consumer pays, the price the firm sets. Okay, and then we ask, would your answer change if the market demand curve had constant elasticity given by P is Q to the minus half? I'm not sure about that. So it should be magnetic. Okay, so suppose consumers prepared to pay Q to the power of minus half. Okay, so let's change that bit, so we have to change this bit. So this is the inverse demand curve, what's the demand curve? Pardon?
PC plus half.
This is Q to the power of minus a half. Someone got it over there? Are you being shy because the video's on? If I stop the video, will you suddenly start answering questions?
T is using minus 2.
Okay, there we go. You will know the answer, you just change it. Okay, it's not okay. So then we have to substitute in PC. Okay. Is that what you said earlier and I just misheard you?
No, I just misread.
Oh, okay, sorry. So this is PF plus T. So we just substituted that. Okay, so let's do the same thing again. We have to change these. Excuse me. We have to change this line. So we're just going to substitute in. Have I made a mistake?
No, just I like this way.
Oh, okay, good. Yeah, plus T minus 2. Yeah, minus C. Okay, so we've got something to differentiate now. We can't use that clever trick on this one. Okay, so at a maximum, naught is d pi d price set by the firm. Okay, so let's use the product rule on this. Okay, so remember the product rule says the derivative of u times v is u dash v plus v dash u. Okay, so u dashed, so we've got something to the power of minus 2, so using x to the n goes to nx to the n minus 1. This becomes something to the power of minus 3, all times minus 2. So we've got minus 2 pf plus t all to the power of minus 3. Okay, and then we have the derivative of what's inside, but the derivative of what's inside is just 1. So that's fine. So this is our u dash. We've got u dash times v, pf minus c, plus u v dashed. Okay, pf plus t to the minus 2 times the derivative of this. Well, the derivative of this is just 1. Okay, so that's easy. So in total, let's collect all these terms. Okay, so we've got pf plus t to the minus 2 all times, we've got 1 coming from here, 1 minus 2 times pf minus c divided by pf plus t. Does that make sense? Okay, so we had this to the power of minus 3 is to the power of minus 2 times to the power of minus 1. Okay, here's power of minus 1, it's just dividing. Okay, and then we've got the pf minus c, and the minus 2 is going back. Does that make sense? Okay, so at a maximum this thing is equal to 0. This bit's always positive, right? If your price is always positive, the tax is positive, something positive to the power of minus 2 is still positive. So this is positive, so this bit never equals 0. Okay, so this whole thing to equal 0, this thing in square brackets must equal 0. Okay, so we must have that 1 is equal to 2 times pf minus c divided by pf plus t. Okay, so let's divide by 2 and then multiply by pf plus t. So we've got a half pf plus t is equal to pf minus c. So now this is just linear, we can do this. So we've got 1 pf here, we've got half a pf there. Let's subtract half pf from both sides and add the c over. Okay, so, sorry, it's a bit of a mess. Half pf is going to equal to c plus half t. That's all right. Okay, so pf is equal to 2c plus t. A bit of work to get that. Okay, so remember this is we started with an isoelastic demand curve. What we end up with is, if there was no tax, we'd have price as something times marginal cost. So we're getting markup pricing, which is what we expect. Okay, isoelastic leads to markup pricing, so that makes sense. What's the effect of a tax? Well, tax isn't quite working the way you'd expect it to. It's just a kind of constant added to the price. So the firm, if you like, is setting the same. So this is PF. PC. Maybe this is the way to think about it. PC is going to be 2c plus 2t, right? Because PC is PF plus t. Okay, so it's like the firm is setting, kind of putting the tax into its marginal cost in this case. Okay, so it's still setting markup pricing, but now it's treating the tax as if it was in marginal cost. Maybe that's the way of thinking about it. That's the effective price the consumer pays. Essentially. Oh, it's fine. Okay, so in the first case, remind me what the answer was in the first case. PF was, what was it, C plus a minus t over 2, is that right? Yeah. So here, tax was having, it has the opposite sign even, it's very different. So here, as tax increases, because consumers are prepared to pay less, the firm has no choice but to reduce the price they charge, okay? Because we're moving the whole demand curve down, the maximum consumers were prepared to pay was actually reducing. Here, as tax increases, the firm actually wants to charge more. And this is because, unless I made a sign error, which I hope I haven't, no, I don't think I have. This is because, yeah, it's because the tax is like an extra cost that the firm has to pay on each unit. You know, it's acting like an increase in marginal cost. You know, so if you look at, remember what these demand curves look like. Okay, they're something like that. Okay, so there's some price at which consumers are prepared to, some quantity at which consumers are prepared to pay an arbitrarily high price. So it's not like the previous case where the tax is going to price people out of the market completely if it's too high. Here, if they just have to pay a tax, they still want to consume some of the good, but they want to consume a bit less. Does that make sense? My computer's gone to sleep in the meantime. Okay, shall we have a go at the exercises from this week, and then if we have time at the end, we'll go back and do some of the extra exercises. Does that make sense? Unless there's something you're dying to do. I know it's not ideal having the class the day after the lecture, you know, I did complain, but okay, so what was it? 2.6 questions 1 to 4. So these are just game theory exercises. 3 major car producers. 6.8. Let's see if there's something more. Okay, so excuse me, the exercises in 6.8 were virtue competition. The exercises in 2 were game theory. So let's do the game theory ones quickly, just to check that everyone remembers their game theory. Okay. So the first exercise, was reminding you what best response functions are. Okay, so I've got to write some games on the board. Okay, so we had, the first game was War and Peace, and it looked like this, War, Peace, okay, and what are the payoffs? 1, 1, 0, 3, 3, 0, 2, 2, 2. Okay, and the question was about best response functions. So I think I kind of briefly mentioned them in the lecture, but just to remind you, a best response function tells you what player 1 would do as a function of if player 1 knew what player 2 was doing. Okay, so suppose I told player 1 that player 2 was going to play war, what would player 1 want to do? Well, player 1 has a choice in that case between getting 1 and getting 0, they prefer to get 1. If I told you this column player was going to play peace, player 1, the row player has a choice between getting 3 or getting 2, so the row player would still like to play war. Okay, so the best response function of the row player, okay, is to always play war. Whereas, let's look at the best response function of the column player. Okay, the column player, if a row player is playing war, the column player has a choice between getting 1 and getting 0, they prefer to get 1. If a row player is playing peace, the column player has a choice between getting 3 and getting 2, they prefer to get 3. Okay, so the best response function for the column player is to always play war as well. Okay, this is just a prisoner's dilemma, isn't it? So here the Nash equilibrium is war. Yeah, that wasn't very interesting. We'll grab the next one. Table 2.3. So here, this is so we've got someone has a choice between opera and football, someone else has a choice between opera and football. Okay, and it's 2, 0, 0, 2, 0, 1, 1, 0. Okay, so this is supposed to illustrate non-existence of a Nash equilibrium in pure strategies. Okay, so the row player, if a column player was playing opera, the row player would rather play opera. If the column player was playing football, the row player would rather play football. Okay, so the row player, Jacob, he likes to do the same thing as Rachel. Unfortunately, Rachel doesn't like Jacob very much. So if Jacob is playing opera, then Rachel wants to go and watch some football. And if Jacob is going to play some football, then Rachel wants to be as far away as possible at the opera. So neither player is very happy, but these are their best response functions. Okay, so the underlying things are the best response functions, effectively. Okay, it's giving you the mapping from what the other person's doing to what you want to do. And there's another one, but I won't go through it again. So best response functions are going to be a useful way of thinking about behaviour in these games of oligopoly. You know, we'll think about, when we solve the Corno competition, we'll think about the best response functions of each firm, and that would be the easiest way of finding the equilibrium.
Is there a mixed strategy equilibrium in this?
Yeah. So there's, so what Nash is famous for is he proved that as long as certain technical conditions are satisfied, there's always an equilibrium in mixed strategies. Yeah, you know Nash from The Beautiful Mind. I guess it's some sort of film. And John von Neumann, who was this famous mathematician, also involved in the Manhattan Project. He was around at the time. So von Neumann had done work on a particular class of games called zero-sum games, which are games like chess, where you know, anything I win, I'm taking from you. Okay, and von Neumann improved results for those. And then Nash came up with his general theory on existence, and von Neumann said, "Oh, it's just a fixed point theorem." So it's almost trivial. The proof of Nash's theorem, you can write it down in a single line. It's like, therefore by Katakani's fixed point theorem, Nash's theorem. It is just a single line for proof, once you know the relevant bit of maths. So von Neumann thought, Nash's work was a complete waste of time. It's just obvious. It's just a standard fixed point theorem that everyone knows. I should tell you what a fixed point. Just out of interest, so a fixed point theorem is, suppose you've got a function, you've got a function from some set to some other set, and you want to know, is the sum x such that x equals f of x? Okay, and fixed point theorems will give you conditions on this function f such that there is a point satisfying x equals f of x. So fixed point theorems are what we use to prove existence to solutions to those equations. That's by the way. I'm going to skip the next exercise because it's boring. And the one after that is very long to explain, so I'll skip that as well. The next one, I'll do exercise 4, okay? Unless people have a burning desire to see the others. Okay, so we've got 3 car producers, C, F, and G. And they've got a choice between producing large cars or small cars. Okay, so that's their action: produce a large car, produce a small car. Okay, and we're calling the actions small, large. So AI is the set of possible actions they're choosing from, and firm I is going to choose action AI. Okay. Okay, then there's this complicated profit function. Okay, profits of firm I are, so they're either gamma, alpha, or beta. They're gamma when okay, so they're gamma if everyone does the same thing. Okay, so either everyone produces a small car or everyone produces a large car. They're alpha if firm I produces a large car but everyone else produces a small car, or if firm I produces a small car but everyone else produces a large car. Okay, so they're alpha if firm I opposite to everyone else. Okay. And they're beta if, well, in any other case. I guess this is CFG. So this they must be thinking of Chrysler, Ford, General Motors. Okay, then it asks us to answer the following questions. Does there exist a Nash equilibrium when alpha bigger than beta, bigger than gamma, bigger than naught? Any ideas? If there is a Nash equilibrium with alpha, when alpha is bigger than beta, bigger than gamma, what does it look like? If not, why not? Any ideas? Well, the firms are all symmetric, so I guess the equilibrium doesn't have to be symmetric. Okay, so alpha is my favourite choice. Okay, so if everyone doing, let's think of some possible equilibria. Okay, suppose everyone was taking the same action. Could that be an equilibrium? Well, no, because alpha is bigger than gamma. Okay. Okay, so should we have a look at these Bertrand questions? Now tell me if there's something that you're not happy with or you want me to spend more time on. What did I ask you to look at? Okay, so 6.84, 1 plus C and D are optional. And we can't do, yeah, we won't do that one, because that's corner as well. Okay, let's do question 4 because that's the only pure Bertrand one there. Okay, so for our end consumers in this market, they want to buy some good. They're prepared to pay anything up to $10. Okay, so each consumer has a valuation of $10 for the good. Consumers buy from a firm selling at a lower price, standard. When both firms set the same price, demand is split between the two. Zero production cost for both firms. Okay, find A and C. Okay, find the Bertrand equilibrium prices for a single shot game. Two firms choose their prices simultaneously. What was the B say? Not much to do really. What under Bertrand competition, what price will they set? Say doesn't matter. Marginal cost is 0. Yeah, so they'll set price of 0. I thought they had some better Bertrand exercises. Maybe in the extras. Okay, so then part C is a bit more interesting. Okay, now suppose the unit production cost of firm 2 is $4, but the unit cost of firm 1 remains 0. Okay, one firm has marginal cost of $4, the other has marginal cost of 0. What are the prices going to be? So the question doesn't say anything about integer pricing. Okay, so if you like the equilibrium, when there's no integer pricing constraint, the equilibrium in Bertrand is that the price is $4, but one firm doesn't sell anything. Okay, so it's like the way to do Bertrand without an integer pricing constraint is to think that firms have two choice variables. They choose their price they set, and they choose whether or not they want to sell. Okay, so the equilibria is firm 1 sets a price of $4 and they sell. Firm 2 sets a price of $4 and doesn't sell, and chooses not to sell. Okay. Why is this an equilibrium? Well, firm 1 can't deviate to a higher price. Okay, because then people so you have to interpret don't sell in the right way. So this is kind of don't sell in the special case in which both firms are selling the same price. Okay, That's what causes for problems. Okay, so if firm 1 deviates to a higher price, people buy from firm 2. If firm 2 deviates to a lower price, they're below marginal cost, but they don't want to do that. If they deviate to selling, okay, then they're no better off. Okay. But you know, $4 sell, $4 sell is not an equilibrium, okay, because this firm would like to deviate to a slightly smaller price. So, you know, doing purchasing competition with continuous pricing properly is actually a bit harder than doing it with discrete pricing. Okay, because there's no such thing as epsilon, right? You can't, you know, the deviation, you know, you might said, okay, so how you explained it was firm 1 sets the price of $4 minus epsilon. Okay, so $4 minus the smallest possible real number, but there is no smallest possible real number. So you need some other way of describing the equilibrium. So rather than saying that demand is automatically split when the price is the same, you say that firms can choose whether or not they sell any goods when the price is the same. Okay, if they both choose to sell goods, then demand is split. Okay, but if you have that extra choice variable, then we can describe standard virgin as a Nash equilibrium. Does that make sense? So this isn't an equilibrium, right? Because he's sharing the market. Sharing the market for $4, you know, deviating to some £3.99 is probably going to be better. Whereas saying the whole market at $4 is happy. Thinking the extra exercises for some better virgin ones. So set 2 and set 6. Let's say. I don't know, this is game theory again. This is corner. Well, let's just. Does this make sense? Should I go through this again, or it's fine? It's fine. Since we spent a lot of time talking about that integer pricing, let's just do an exercise on the board with integer pricing, okay? I'm not going to say anything, you can tell me all of the equilibria. Okay, maybe we've got let's have 2 firms to start with. One with 97, one with 100. Okay? Pricing in whole numbers. What do the equilibria look like here? Okay, so 99 and 100. Okay, so this firm doesn't want to deviate upwards because then it's sharing the market. This firm doesn't want to deviate down because then it would be selling below marginal cost. Yeah, so this is an equilibrium. And for any others? 100 and 101. Okay. Again, if this firm deviated down, then it's currently making 0 profits. If it deviates down, it's sharing the market, selling at marginal cost, making 0 profits. So it doesn't want to deviate down. So this firm's happy, this firm doesn't want to deviate up or down. Are there any others? What about these funny ones? So one firm is pricing below marginal cost, which is a bit weird, but still, as long as the demand curve is downward sloping, this firm doesn't want to deviate upwards. This firm is making 0 profit. It doesn't care if it's pricing below marginal cost. So this is one as well. Is this one 97, 98? because this firm is currently making 0 profit. If it goes up, then it's making at least some profit. So that's the gist of these things. What about some examples with 3 firms? I know you've done these things to death, but I don't want to give you the same example, but we just have okay. What about that? 4 firms. Can we handle 4 firms? Give me an equilibrium. So what prices can this firm, the first firm set?
201.
Okay, let's try 201. Okay. Suggestions for the next firm? 202. Okay, and you want these higher, do you? These don't really matter. Okay, well that looks promising. This firm deviated downwards, they'd be selling at marginal cost, so still getting 0 profit. If this one went up, they'd be splitting the market at a higher price. As long as demand's downward sloping, they'll be worth some. These firms don't want to deviate, so that looks fine. Are there any in which firm wants at the price of 200? What about, can we sustain? Probably not, I suppose. 200. Yeah. No. So they would always want to go up.
2 at 100, 201. 2 at 201. Both first firms use
201. Yeah, so if either firm deviates upwards, then they're sharing the market at a higher price. Yeah, as long as they have downward sloping. No, they can't deviate up because then they get nothing.
Yeah.
This one is selling at marginal cost, these are different. This one doesn't want to deviate down because then there'd be a marginal cost. Okay, so that looks okay. Can we get one with 202? Does that exist?
I think so.
So this firm would also have to be at 202. What about this? Well, this depends on the demand curve, doesn't it? Okay. So this firm is currently getting half the market at 202. They have the option of getting the whole market at 201. So if the demand curve is totally inelastic, then this equilibrium exists. If the demand curve is downward sloping, then they'll always prefer to get the whole market at a slightly lower price. Okay. So this is, I'll give this one a question mark. Okay, it depends on the demand curve. Just change it a bit. What if this firm, we have 2 both with marginal cost of 201? You were looking very miserable. Some kind of early in the term. Oh, I don't want to be here. I feel the same way. So that, well, we're going to be a few. So, 201. No, that's above. Is that the only one? That's only an equilibrium, right? So these 2 firms are happy, they're getting their £1 of profit. They deviate down, they don't make any profit at all. And I guess I've got to stop.
Can they both sell at 203?
Can they both sell at 203? Well, then they're splitting the market in 3, right? Oh no, yeah, possibly 203, 204. That looks promising, doesn't it? It depends on the demand curve, right? Whether they want to deviate down. They're making £2 profit with half the market or £1 profit with all the market, so it depends on the demand curve.